So what I'm going to talk about today is concurrency and a very nice library for doing concurrency called GPars. So I'm one of the committers to Groovy and one of the committers to GPars, so I know a little bit about it. I'm only going to be really touching I haven't got time today to really just give a very quick overview of all the features that are in GPars and things you can do with concurrency. Even though I don't really have time, I've also got a little bit of intro material on concurrency in the talk, which is basically warnings on the path that concurrency can lead you on. And it's kind of like the Chinese proverb, or what's assumed to be a Chinese proverb, but I just tried to track down its origins and no one knows where it came from. But may you live in interesting times, and it's sort of both a proverb and a curse. Well, I can tell you that concurrency is very, 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 very interesting. So let's get started with that particular topic. Okay, so we're going to do a bit of intro and then dive into GPars, and then I've actually got 3 examples at the back. So all the slides on these will be on SlideShare. There's a version there which is a 1.5 hour talk already. I'll put the revised one up probably on the way to the airport later on this afternoon. And all the source code is actually a very old thing in GitHub somewhere, but I'll put a brand new, fresh version of all the source code and all the examples you see here on GitHub. There'll be additional examples there. There's a dining philosopher's example in about 4 or 5 different paradigms that you can go look at. We won't get time. There's a testing. I use concurrency with non-developers all the time. We set up testing DSLs and we show them, type in these 5 characters, .parallel, at the front of your test, and it'll all be in parallel, and they kind of go, oh, okay, and they type this stuff in, and they've got parallel test suites that used to take an hour to run, and now run in 10 minutes and things like that, just by using these features. So these features are very accessible, but you can easily also get yourself in lots of trouble, so you just have to be a little bit careful. So I guess this is where you normally do the pitch of concurrency is coming, you've all got multi-core processors, if you don't do concurrency now, you'll be out of a job in a week. I don't really believe that. So I won't give you that pitch. Concurrency is coming. We've found lots and lots of ways to avoid concurrency a lot of the time. So going back to the initial thing, concurrency is interesting. If you want a less interesting life, don't look at concurrency. There's lots of ways to avoid it, and you should probably do that. If you do get into concurrency, there's lots of simple ways to do concurrency. I'm going to encourage you very, very strongly to go down those simple paths, and I'm going to show you some of the options you have in the simple paths. I'll also very briefly show you the more complicated options. So you'll go to some talks and they'll say, you must do everything as an actor, and every single program you write from now on, you should write as an actor or whatever, because that's what their framework supports. GPars also supports actors, and it is a very, very useful paradigm for certain problems. But it actually doesn't come for free. It's got some complications. And if you start using, I'm not going to just pick on actors, I'll pick on all of the complicated paradigms. If you start using them willy-nilly without putting your thinking caps on, you can just as easily get yourself into trouble as if you avoid concurrency altogether. Okay, so why are there lots of hard ways to do concurrency? You've probably all learned about them early days of computing if you ever tried to get into this space. You have to deal with threads and locks and semaphores, and it's an exercise later on to do before you can have lunch, that you've got to write the dining philosophers using semaphores, and if you don't get that done, and if it doesn't deadlock and doesn't live lock and whatever, then you won't get your lunch. So we'll come back to that. So there's lots and lots of complicated ways to do things. Turns out we've learnt a lot. We've learnt a lot in terms of immutability. We've learnt a lot in particular kinds of algorithms that lend themselves really, really well to doing concurrently. So you've heard of Google and things like MapReduce. Hey, it turns out that many of your algorithms, if you can tweak them a little bit, express them slightly differently to what you're used to, there's some things you can get a very, very big bang for buck, get some concurrency, and go a really, really long way without getting too much trouble. Okay, still lots and lots of ways. If you Brian Goetz's book, if you want to find out how the painful details of going down to the lower levels of concurrency, go and read this book. I'd advise you to if you get depressed easily, take your medication before you read the book. Take additional medication after each chapter. It is a very, very interesting book. There we go. Okay, so there's lots of. I shouldn't be too negative, because we do know a lot. We do know a lot of things that we can do now to gain a lot from concurrency, and some of them are very, very easy. And there's lots of different options. And it turns out that some of them are complicated. So there's lots of, you can go and, there's lots of advice you can get on doing the simple things. And there's a new book from Ralph Johnson and co, he's one of the gang of 4, that talks about patterns for concurrency and patterns for parallelism. And this is sort of one of the things that's at the start of their book is, yeah, these are the ways we used to do concurrency, and there's slightly less complicated ways like actors, slightly less complicated things like fork joins, slightly less complicated things like data parallelism, and he encourages you very strongly to move down here. Well, I'm going to also encourage you to do that, and we'll have a look at data parallelism. We can talk about specific details. Some of these approaches are very non-deterministic. What that means is you've been told to write test suites. If you're in a non-deterministic system, most of your test suites won't be any use to you. But there's ways we can actually solve that as well. Some of the things that I'm going to tell you about actually turn out to lend themselves to allow you to write tests in the way you've written them before without having to worry about the non-determinism, so futures and things like that. Okay, so the main thing I'm going to try to come back and show you after a few more little warnings, I feel that it's a public obligation to give you enough negative feeling about this concurrency area, because if you go into it and expect to gain lots of things, doing complicated things, you probably will be a bit dissatisfied. So I'm going to do a little bit more on that intro, and then we're going to come back and look at the features of GPars. There are other libraries around, so I'm not just telling you on GPars. There's an ACCA library for Scala. GPars you can use from Java, Scala, Groovy. It's a very, very useful library, and I actually think it's slightly ahead of most of the other libraries in terms of the ability to give you big bang for buck, simple ways to do things as well as the complicated ways to do things. Okay, so we'll come back and look at each of these facilities and when they're useful and what they're good for. We could spend a whole hour that we have here available just talking on this one slide. I was almost tempted just to put this up and see how far we could get just talking on this side, but I didn't. I thought you might like to see code samples and things like that, so I refrained from doing that. So the flip side of that is I won't be able to give full justice to this particular picture, but go and look at that Ralph Johnson Parallel Programming's book. It's got a simplified version of this. This is a version specifically tweaked so that it's got all of the capabilities that are in GPars catered for. It is worthwhile spending just a couple minutes on this picture though. So what are the things you need to be going through in your mind? This will all be on SlideShare, so by all means take pictures, but it will all be in its original form available for you later. So what are the things that need to be going through your mind when you're looking at concurrency? If you start thinking of frameworky things, actors, DataFlow, whatever, that's the wrong way to approach this. You've got to be thinking about your problem at hand. And so the first thing you should ask yourself is does it fall into, I've got even the wrong wording here, perhaps for what I've just told you. The advice I've given you, I probably haven't followed fully here. The problem you have at hand, do you have a large parallel amount of data that you can do a single algorithm on for each of the pieces? So independent pieces of data. So I've got 1 million records, and for each of those records, I want to do one thing and end up with another 1 million records, or I've filtered those records, or I've transformed those records, or something. That's data parallelism. If my data is truly independent, I can just set my cores going off and saying, yeah, here's the algorithm I want you to do, here's all the data, off you go, do all that. Okay? If it's of that nature, that's very, very good. Then there'll be certain approaches to concurrency that will lend themselves to that, and that's where MapReduce and things like that will come into play later on. Do you have task parallelism? So I've got 1 million tasks that I want to perform, and they all have independent data. Well, just farm them off to my cores, and off they'll go and do their independent things, if they're independent. Okay? Turns out there's a lot of programs that aren't exactly on those two axes, and they're a bit of both or whatever. We'll get to that as we go along, but your biggest bang for buck will be identifying ones that fall closely to those two axes, and if you can, and that's what I'm going to do, spend the last half of the talk on. We're just going to go through one example. I'm going to show you how to take something that's not of this nature, I'm going to turn it into a data parallelism problem. It's not independent data, we're going to make it so that you can do it. And that's the kind of thing that you best do. So you'll get best bang for buck if you can convert the thing that you need to solve into something that's very, very close to one of those two extremes. Okay, so don't want to go into too much on the rest of the detail, but it turns out if you've got data And turns out the data, it's not quite just a million records that are all fully independent, but if the problem can be expressed in such a way that, in order to solve a million records, well, if I solve this 500,000 and this 500,000, and to solve this 500,000, I can do this 250,000 and this 250,000. If you can express it that way, the fork join algorithms end up giving you nice, elegant solutions, and you won't shoot yourself in the foot. They lend themselves very well to that. Parallel collections is where MapReduce and things like that fall into that category. I didn't really mention this whole fork over here on the right-hand side. Stream data is just, it's sort of like data parallelism, but I've got a stream of data going down the pipeline. It's got some slightly different characteristics, and there's certain things, certain kinds of data flow operators and things that lend themselves to that. Actors can, if you've got a regular data, actors are actually a pretty good solution to that. Remember, actors are starting to get a bit complex, as are some of these other ones further down this diagram. They're starting to get a little more complex. So you don't just dive into those unless maybe you can convert it to something simpler, and you'll go a long way further. For task parallelism, if you've got, again, if it's sort of linear tasks, that all the tasks are very, very similar, symmetric sort of thing, there's a certain range of solutions, and we'll have a look at some of those. If it's recursive, so it's sort of like I said, splitting the problem up, if you can split your task up into smaller things, fork join comes back into the equation here. So I've got data and task as different axes here, but they're duals of one another. So they're not independent things. I want to run an algorithm on some data, or I've got some data with an algorithm to apply. They're just duals of one another. And we'll briefly talk about some other things. So good to use immutability if you've got sort of ad hoc things to do. That have to actually share data. If you can, make as much of the data read-only as possible, and we'll find out that we can go and even use old synchronization techniques. We'll get to that one. If you need to. It starts to get quite complex going down that path. A different way to think about that particular graph. Sometimes it's hard with that many decision points sort of flowing down. Just think about the problem you've got at hand and how you coordinate the different parallel things. Okay, so it turns out the data parallelism things that I'll show you first, so you get a lot of bang for buck, it's just fixed coordination. It's, as part of the approach, of taking that approach, the coordination happens for you. You've got no choice in the matter, it's not explicit, you don't see anything, it just happens. With actors, you're deciding to take control of how concurrency is going to play out. So at any particular point in time, by one actor sending off messages to other actors, you know exactly the amount of concurrency that you're going to be forking off, and then you go to another actor and it forks off things. And so you're, as a programmer, are explicitly going to say where the concurrent activities are going to be. We've got a thing called safe agents. So it turns out, if I fall all the way back down to Java's concurrency capabilities, I've got a lot of work to do, and I've got to know what I'm doing, or I can get deadlocks and live locks and things. We can just delegate that to some agent that knows how to do all that sort of stuff. And I'll show you that very briefly. And DataFlow. DataFlow is a very, very important one. It's turns out to be one that's got very, very nice properties. You end up with very, very elegant code. It's the declarative style. So we saw in Damien's keynote, declarative is a really good way to go. DataFlow gives you that, and it's very, very simple to do, and we'll see a very simple example of that. Okay, so remember I said avoid concurrency if possible. Well, you can do concurrency by separate processes. You can do fork off ant and exec things and spawn things, and so there's ways to avoid it. So we can do that if you can, but oftentimes you can't do that. If you do need to do the low-level stuff, I'm just going to briefly mention some things. There's lots and lots of ways to get the sort of parallel design patterns wrong. And Groovy has gone and, this is no GPars yet, Groovy's gone and built some WithReadLock, WithWriteLock and other annotations that actually do all the right things that you need to get right. Okay, and they make it really, really easy not to get it wrong. Okay. So I advise you to go and look at those. This is sort of showing you some of the code that it would produce. Well, that's not important for us today. Who's used the synchronized keyword in Java? Yeah, you're like me, you've also written bugs. So if you use synchronized, that's a bug. So don't do it. Groovy's got a nice way to get around it. So does anyone, just very quickly, anyone know why it's a bug? So if you use synchronized as the keyword, the modifier, right, not as a block, then it'll lock on your instance, this object, this. And anyone else in the system pointing to this object? Well, if they are, they can deadlock you. If you do a static synchronized on a static method, what's it locking on? The class. Anyone get access to your class, they can do locks, they can deadlock you. You will not know. So that's sort of why it's a threat. So you want to go and use a private lock, and this will make that happen automatically for you. So there's ways to not make it so hard. And that just shows you the details. We don't need to do that. If you've ever trying to do lazy initialization, there's lots and lots of ways to get that wrong. Go look in the book again. Take your medication first, your depression medication. Even if you don't ever get easily depressed, I'd advise to go get some. It tells you, there's pages and pages that tell you how all this stuff breaks. Even when we thought the JVM was going to do the right things for us, that the JIT inlining moves all the order of all the bytecode around, and things that we thought were atomic operations, they're not. Maybe they're not there, or maybe they're not atomic anymore. Maybe we're in an order that we're not expecting. So there's lots of ways to get it wrong. There is a preferred way to get it right, and Groovy gives you nice, easy ways. This will produce the recommended ways to do those sorts of things. So there's some good things to look at. On the immutability side of things, again, this is orthogonal in some ways to GPars. If you're writing stuff where you have to do some shared data yourself, you can go use collections. You can go use Java's collections, the ones out of the standard util libraries. There's some things to make it easier for you. There's an as immutable. If you don't like the built-in stuff, you can go get Google Collections. It's got a whole bunch of immutable stuff. We can do special meta-programming stuff to make things more immutable and all sorts of things. Probably, I'd advise you, the only thing that, there'll be persistent classes and there'll be this immutable thing are the two main things if you ever go and have to roll this stuff yourself. So who knows the rules for writing immutable objects in Java? I'm sure some of you do, yeah. There's 27 rules or whatever, and I'm sure you recite them each night before you go to bed. But yeah, so you've got to have private methods, getters, no setters. You've got to write a hash code in terms of your fields here. You've got to write an equals that's compliant with your hash code. You've got to have defensive copy and defensive copy. So there's a bunch of rules. Again, Groovy gives you nice, simple ways. It says just write that, and I'll do the rest for you. So the intent is a lot clearer. Just doing things like that. So there's some things you can go look at. Who's heard of persistent collections? So anyone want to give me a definition of persistent collections? It's got nothing to do with Hibernate, if you've heard of things like this. It's not persisting to a database.
Can you say it reuses part of its structure, making copies?
So whenever you create something, that persists in time, and when you create something new or something slightly different, it points to here's the old stuff and here's the bit I changed, or whatever. So, yep.
It makes some very good
yeah, and in fact we can, glad you said that, because on the next slide I'll show you how to use closures, persistent data structures. You can actually use, there is a few persistent collection libraries around, and closures you can use from Groovy, at least the early versions. There's a port that will make it, future versions you can use as well. There's a thing called P collections, which does just this. Now, if you don't know what persistent collections are, this is just, I'll go through this little picture, and I've got a bit of poetic license here, but if you're using Java's collections, you'll have some pointer to a collection of things, and underneath the covers is sort of an array of characters or whatever in this particular case. So I've got C and A here, and I want to add a T. What do? We end up with a pointer to the exact same implementation array that we had before, but we've got another character in there now. So this is mutable. What's wrong with this? Well, if I'm writing and someone else is writing at the same time, we might both be trying to stuff a new character in the one spot. If I'm in the middle of writing stuff and someone's reading it, what are they going to get, the old stuff or the new stuff? So we know how to do locking and synchronizing on this, but it's work. It's lots of work. So one of the solutions is to go and use immutable collections. And what would they typically do? Well, they probably have the same stuff underneath. But what they do is, when you say, add a new character, they throw away the old thing and create a brand new thing under the covers so you can't see what's going on. And you end up with just a brand new array, and anyone who wanted to have the new thing will have to point to this new thing. So you've still got a problem here in that someone somewhere has to manage all the pointer references to the old things. Okay, so this doesn't magically cure your problem, it just moves it to somewhere else. And if you went back to the million records problem, if I was creating strings or collections of characters that were millions of lines long, I'm going to throw away 9,909 and expect them to be garbage collected and whatever. So this might not be very efficient. So some people will tell you have to go this way. Not all algorithms will work well if you do that. Sometimes it's better to go old school. Now, what persistent collections do is they keep old stuff around. Old stuff persists. And I've used a bit of poetic license here in that it's actually going to be persistent collections all the way down. It's turtles all the way to the bottom. But, so in fact, this will probably have one character and point off to just an A and so on. But we'll ignore that. So now, is this better? Well, yes, it's going to be much more memory efficient. But it turns out that there's problems with this approach as well. What I end up with is very, very dense hierarchies of graphs, potentially. And someone comes along and says, oh, I'd like to sort that now. And you've suddenly got an immense data structure with links all the wrong way, and you've got to go and work out a way to sort that. So you can go and look up the research, the research that's going on here, and they'll tell you which operations you can do on these sorts of collections and what the performance characteristics are going to be like. Certain operations like a delete or a sort or whatever might be very, very inefficient. Now the good news is there's lots and lots of research going on to find really efficient ways to actually have, well, here's one set of pointers, now I'm going to make a sorted set as well and not touch the other ones. And so we're finding really, really efficient ways to do these things. So over time, this is going to become a better and better option for you to choose, but we're a long way from there. So people who come and tell you, go and move everything there now for every single algorithm, I don't necessarily believe everything they say. Yes, it's a very good thing to go look at. It still has lots of things we need to solve. Okay, there's lots of stuff going on. It's a very interesting area, but don't get fooled into thinking it's going to solve all your problems. So I'll have huge graphs of stuff. I've got pointers all over the place, and I've still got to manage those things. I've moved the problem in a slightly different way. It's got some really, really nice characteristics, but we haven't solved the thing completely. And here's going and using some of these sort of different collection libraries. This one's a totally lazy library. This is the closure library, so closure's got some really good persistent stuff in. Scala's got some good. You can use either of those from Groovy as well. Okay, so that was just brief look at that stuff. So still got a lot of material to get through. We're going to start coming now and seeing. So most of the stuff I was showing you was down in this sort of area. This is sort of fairly low level, doing sort of more ad hoc data sharing. Sort of the old school way. What we want to look at now is some of the ways that you get better bang for buck. Okay, so these examples are always a little bit contrived, I think, but just bear with me because it's at least a simple example that hopefully we'll understand and see how it goes. So this is some sequential code. Okay, I'm going to take the numbers 1 to 30, and what I'm going to do is square them. So I've now got a bunch of squared numbers. And this is a little regex operator in Java. It's not important. But what this is saying is, of all the numbers that you've got, ones that start with 1 and then have some other characters, collect those, find all those ones. So what this is going to do is I'm going to take all the original numbers and then find all the ones that start with 1. So we're calling this the 1 starters. So I run that and it comes out 1, 1600, blah, 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 up to 196. Okay? Then I can do some other things. I can find the max of those numbers, which is obviously 196, or I can sum them, for instance, 747. I was on a 747 as I was writing this, so I kind of had to stop the example at that point. I'm not allowed to change it anymore. I'm on a 747, I don't want to cause any trouble here. So this is all sequential. So how do we make this parallel? Don't know if you can see what we're doing here is, but all these methods, so collect, find, max, and sum, you just say parallel, right? And I've got a bit of a pool thing around here. This basically, if I'm on by default, if I'm on a 4-core processor or a 6-core processor, it'll actually give me, actually the default's the number of cores you've got plus 1. There's many algorithms, you have sort of a main line and then you're forking out. So it turns out to be a really good useful example, but you can in brackets after with pool say 10 or 2, right? So depending, if your program is doing lots of I/O, it's actually useful to have more cores, because some of those cores are going to end up waiting for stuff. If you've got a very, very CPU intensive thing, it's usually no value in having anything smaller than anything larger than your number of cores. But you may actually want to go smaller than your number of cores if you know that you've got other things that you need to be doing and you want to leave them a few cores, right? You don't want to totally take over your machine. So I could say 3 here, and it would leave a couple of cores hanging around that I could run other stuff on. But we're just going to, all the examples I'm going to give you are just going to use the default. Okay. So what actually happens here? It goes and forks off all the cores and does the same operations that we did before. Okay. So it's what can go wrong? Can there be any deadlocks here? Can there be? No. Right? So did I understand the algorithm when it was sequential? Okay. Do I still understand it when it's concurrent? Well, probably, right? So there's the level of complexity that doing this concurrently adds is very, very small. Okay? Now, it turns out there's some variations of this, and I don't really want to go into. Oh, well, actually there. Let's look at when won't it work? Well, if my data wasn't independent, this won't work. So if I was doing factorial or Fibonacci or something, where one result's got to depend on earlier results, this isn't any good to me, right? But I get really big bang for buck if it is independent. So I've got a fairly simple algorithm. I can apply it across all my data. Really good bang for buck. Almost no complexity. Almost nothing can go wrong. Okay. Now, will it actually be faster? Do you know what? For this particular example, it's about a 50-50 chance that it'll be faster and a 50-50 chance it'll be slower. It's the kind of thing that the JVM can really, really heavily optimize. And even when it's doing its stuff sequentially, it's actually pretty, very fast at doing this sort of stuff. And the overheads involved with splitting this thing up and doing it concurrently about match the gains that you get for this particular example. If I start boosting the number up to 300, 3,000, 300,000, I do start getting very, very significant gains. But for something as small as 30 numbers, don't get very much gain at all. It actually turns out to be about twice as fast in this particular example. But not 4 times with 4 cores or 6 times with 6 cores. Now, there are some variations on this. If I didn't like having parallel everywhere, I can use a bit of Groovy metaprogramming and make that go away. I can make concurrent, make sequential at any point. And then turns out this is really nice because now the code that's inside here is identical to the sequential one. Okay? So I can actually do even this make concurrent outside in some sort of wrapper code, and then the algorithms that I do can be identical whether I wanted them sequentially or concurrent. So that's really nice. And there's also another metaprogramming trick we can use to get rid of this with pool stuff. So I can make certain variables that I have automatically have a with pool that will automatically get put in place for me when I need to. The details of that aren't really important for us today. Now, I showed you find all and collect. Is that right? I showed you max and sum. Turns out there's quite a lot of these. So if you've done functional programming, you've seen folds, you've seen grouping, you've seen splitting. There's a whole bunch of these that you can do. And there's parallel versions, there's transitive versions and lazy versions. We won't need to go into the detail. The documentation is fairly good at explaining all of those. Okay, now, you've probably heard of MapReduce. In fact, the example that we saw was kind of a MapReduce already. So what's this MapReduce thing? Who's heard of MapReduce? And so you've all heard of it, but who would be able to give me very, very eloquent and simple definitions of what it is all about? Surely, yeah?
Maybe a transforming linear filter?
Very, very close. Yeah. That's not bad. So it turns out that I'll skip ahead 2 slides, and we'll come back to the one we skipped in a minute. If we have some data, some parallel data, and we want to transform it, or do a little tweak to it, or there's a few things, we might be doing some aggregation or something to it, or that's kind of the mapping phase. Okay? It's actually probably map filter reduce is probably a better name for it, because usually you have filtering as well. And some people actually classify each of the sections even more with more fine-grained terms, but we won't go into that. So mapping just takes an array of data, does something, produces another array of data, typically the exact same size. And it can be some sort of transform. So this is when you have that algorithm that's the same algorithm across all your data. Then I've got filtering. And filtering typically says I've got an array of data, and some of it I'm interested in, some I'm not. So I'm going to just cross out the ones I'm not interested in, and I'm going to produce another array of the stuff that I really was interested in. And that's filtering. And you typically can have many maps, and then many filters, and then often you'll then do a reduction phase, which the reduction phase is just, I've done all my calculations, I've got all the stuff that's interesting, show me some aggregated value of some kind, some result that I'm interested in. So I might be looking for all my customers who buy the most things, and then the reduction might be, now add up what they actually bought. I want to see how much my big customers buy off me. So the reduction phase, you'll be going and doing some processing. The reduction just says, yep, all that stuff you worked out, sum it all up for me. Okay? It turns out that can often be done in parallel as well. So the sum, when I'm adding numbers, If I've got 4 numbers to add, well, I can just add 2 of them, and then I'll get 2 results, and I can just add those 2 results. So I can usually do that concurrently very, very efficiently as well. So that's all map filter reduce is all about. Now, when I showed you find all and collect, it was actually, well, you can actually be using map reduce type things underneath the covers. So Java 7 has parallel arrays. GPars has a backport of that for Java 5 and 6. When you're doing those find alls and collects with the parallel, it's actually using those parallel arrays. Groovy, GPars also has map reduce filter type methods. They actually they go into parallels and just stay with parallel arrays. Okay. If you don't use the map and reduce that I'm going to show you about now, and you use the collects and find alls, in each phase it goes and converts it into parallel arrays, does its magic, and then converts back to a collection for you. And then it'll go and do its magic and produce another collection. Whereas if you use the map and reduce that I'm about to show you, it's the same as we saw with collect and find all, but it stays as a parallel array for the whole journey. And there's some optimizations to do with scheduling. I can actually start future maps and transforms and things potentially using that approach. I won't go into the specifics of that. Okay, so these are the methods that come with map and reduce. Okay, it's very, very similar to the stuff we saw before. These just stay around using parallel arrays. Okay, so we'll use map and reduce and things like that, whereas we would use collect and find all and things like that, and that's the traditional names in Groovy for those things. So 2 different operators do the same thing and achieve what we had before. So we just have map and filter here. This is now going to produce my 1 starters like we saw before. Instead of collect and find all, produces the same things. Okay, so I can do max and sum just like I did before. If I want to show sum in longhand, I can use reduce directly and show you how reduce works by just saying, yeah, I want to reduce using plus. And that's in fact how sum is defined. Yep, that all makes sense? So, big bang for buck, if your algorithm falls exactly into this particular nature where same thing across all my parallel data. That's what it looks like. Okay, so let's change directions now. I've been told to do a mathematical equation of some kind. I've got functions f1, f2, f3, f4. It doesn't really matter. I've gone and defined them as return itself and return the sum of 2 things just to have some definition. But the definition of what they're doing isn't important. What I've got is I've got a variable a, happens to be 5. That's not important either. The end results could be 10. That's not important. So the important bit are these 4 lines here. I've been told I've got 4 functions to go and calculate. And actually, I've got 4 cores here or whatever, so I should just be able to toss them off to the 4 cores and run, and it should be 4 times as fast. Does that sound like the right thinking of what might be happening? Hmm? Aha, all the right wording, yes. So we've got some dependencies here. Some of my calculations, so F4 here has got B and D as its inputs. Oh, okay, so before I can run F4, I've got to go and calculate B and D. And they're actually the results of some other calculations. So some of my calculations are dependent on other ones finishing. Okay, so this actually is quite complex. How do we work out how many cores, who knows how many cores I need here to maximize the concurrency? Turns out to be 2. How on earth do you work that out? Turns out you just draw a task graph, and that's just, just go and look at the different things. So we've got F1 has A, it depends on A. F2 also depends on A. Right, it produces C, and F4 depends on F1 and F3. So this is my little task graph, and there's only 2 paths down this thing. So I can never use more than 2 cores on this particular thing. Well, I don't gain anything by using any more than 2 cores. Okay, so how would we go and do this operation? There's lots of, I could go thread.start and fork off things, but it turns out there's a fairly simple way to do this using GPars, and that's what's called asynchronous functions. Now the nice thing about asynchronous functions is I can actually, with functional programming, you can merge functions together, you can compose functions, you can curry arguments and so on. If you move to asynchronous functions, you can do all those things exactly like you do when you're doing sequential. You can curry parameters, I can compose the different methods, and when I go and run them, they'll just wait for their input data because they're asynchronous. Right? So there's some very, very nice properties of this. I'm just going to show you one really little example. So what I do here is, I've still got my pool. I know that I can only use 2 cores, so I'll actually go and set it here in this particular case. Instead of saying B was calling F1, what I do is I say I'm going to call F1, but call it asynchronously. And there's actually about 4 different options here. I can, but I'm just going to show you one, and you can go look up the doco for the rest. So I'm just going to say, yeah, call F1 asynchronously, please. And it goes off and does that in another thread for me. Okay. And what I get back isn't B directly, but it's something that knows, it's a future of B. So when it's finished, I call get on it, and at that point, if it's actually finished the result, it'll give me back the result, or it'll just wait around. It'll then be synchronous at that point, and it'll wait. So what I can do is, yeah, future B is just F1, asynchronously call, using that parameter. Now let's stop, while that's happening in another thread, let's continue on with our main line, do some more stuff, and then the final function F4, it'll be future B.get, so that if that's not finished calculating, it'll wait around, and we pass in our other parameter. Okay? So this is explicit coordination. I'm involved in doing stuff here, right? So let's have another look at a different way to do this, and we can use the DataFlow capabilities. Okay, so there's a few DataFlow libraries around. If you're not a Java or a Groovy programmer, then there's lots of DataFlow libraries around. What we do with DataFlow is declaratively specify the things that we want it to calculate. So here we say, yep, ignore again, we can ignore the bottom top lines for the purposes here. B is just F1 with parameter A, C is F2 with parameter A, and we just keep on doing our things declaratively, and that's it. We don't need to do any more. It goes and works out the dependency and whatever. What if we change the order of these things, swap the order around? It doesn't make any difference to our program. It's a declarative specification of the relationship between our input and output. So we can change the order around here and it doesn't make any difference. They're just declarations. We just run that and we get our result back. So this was what Damien mentioned in his keynote, saying that this is a very powerful thing. It is very powerful. This is how I can do the Latin and reverse the things around. It doesn't make any difference. You can go do that yourselves using DataFlow. There's some really interesting libraries around. Okay, now is DataFlow the solution to all problems? Well, this is just some more examples. I'm going to add 2 numbers there. I'm going to multiply 2 numbers there. Okay. Here's some more complex things. So I'm going to multiply 2 numbers are added, 2 numbers are subtracted, and get a result. Okay. Again, you can swap the order and it doesn't make any difference. I'm going to get on to streams. Actually, I probably didn't want to do. I'll do streams. There's another point I was going to make, but it's in about 2 slides' time, so we'll make that. So, DataFlow are variables you can set once. So the best way to think of them is a buffer of size 1. That's a good conceptual model if you're trying to think back to if you've never learned any programming before, just think of DataFlow as a declarative way of doing things. If you're trying to put it back in terms that you've learned before, trying to sort of ground it in things think of a buffer of size 1, when you try to pull something out of it, if the buffer hasn't been filled yet, you're not allowed to, you've got to wait, and once the result is filled, it can't be filled anymore. Okay? So if I go and do something naively, I've got a bunch of numbers now and I want to add them, and I just do the exact same things I did before. The first time I set A, I'll fill the buffer. The second time I do it, it actually comes out and says, no, you can't assign this anymore. Okay, so if you're using DataFlows naively, they don't solve all problems, right? But it turns out that we know about these sorts of problems, and there's provisions for doing streams of data. Okay, and they're buffers that can get reset as the stream is flowing through. And this is just an example of doing that. I didn't really want to go into the specifics, but we're feeding in a stream of numbers here into that calculation we saw before, and we get a stream of numbers out. Okay? And it's all declarative in the way you express things here. Okay, so what's nice about DataFlows? It's inherently safe and robust, right? So no deadlocks. Right? Actually, that's not true. No live locks. It's robust and there's no race conditions. It's amenable to static analysis. So what that means is I can feed my program into a tool that can go and detect many, many cases of typical examples of when deadlocks can occur. And it'll say, yep, I found a deadlock. And there's lots of example programs. Not many of them are super accessible. They're often research things. You've got to go and compile them yourself and all the rest. But they're there. You can go use them. you end up with fairly nice looking code. It's very declarative. Okay? Now the nice thing, remember we said before, throw away all your test suites if you're using non-deterministic things, because the test suites might run some of the time, but they may not run other times. And it might be very hard to produce the conditions for when they don't run. I don't want you to throw away your test suites, by the way, but be aware that they're not going to prove that your programs don't have any problems. If you start using DataFlow, test suites come fully back into the fore, in that if I've got a particular condition like a deadlock, and here's a deadlock here, so flow X is going to wait for flow Y to finish, and then flow Y is going to wait for flow X to finish. You can, if you write a test case for that, it'll fail every single time. Okay? If it passes, it'll pass every single time. Now, there's some, you can actually make non-deterministic deadlocks that can't be easily analysed, but you've got to go out of your way to do it. It's actually quite tricky. We've got some in our test suite, and you have to put a lot of effort into using random numbers and doing a various bunch of things in order to make that sort of thing happen. There's a little example of a sieve. We'll skip over that for today. This is going back and stressing the different kinds of coordination. I want to skip over that. So I've just got some examples of actors. Now, actors are a really, really good way to solve complicated systems. I've shown you ways to not have to even need to get to the complicated things. And so you're much better off using things like DataFlow or data parallelism if you can. Okay? If you end up with something that's a little bit more complex, actors are a good solution, but there's lots of ways in which your actor code can go wrong, and most of the people who are sort of promoting actors at the moment don't tell you about a lot of the different ways. There's a bit of intro material here. You can come back and read that off SlideShare a bit later on. There's a life cycle for actors. It's not dissimilar to if you've seen the life cycle in servlets or EJBs or something like that. It won't look too dissimilar to you. I just wanted to show you some examples that I think that'll give you a better feel for how you can use actors. So actors is all about creating objects that send messages to other objects. If you've got that paradigm in your head, that's the specifics. Now, each of the different actor libraries have different specifics. There's no sort of one standard for actors at the moment. So on some of the libraries, it'll be called, you'll write an on-message method. On other ones, you'll have a different name. Other ones, it won't look like that. It'll look like a DSL flavored thing. So there's quite a few options. In fact, GPars gives you 4 or 5 options as well, as it turns out. And this is where the complexity starts to come in. Depending on your particular problem, different styles of actors, ones that keep state, ones that don't, and so forth. It'd be nice if we could not have to worry about things like that, but it turns out it's still important for the implementations to know some specifics like that at the moment for them to do things efficiently. So there is you've got to have your thinking cap on when you're using actors. You've got to, if you choose the wrong one, you can end up with much less efficient solutions than you need. So, and this applies to all of the libraries. I'm not, so GPars I think does one of the best jobs of making this simple, but yeah, there's certainly even options available in GPars. So this is, I'm going to first of all show you a style of writing writing actors that's probably familiar to you, and it'll look like we're writing a servlet code. Or JMS code or something like that. So if you've used Java EE or something like that, so we know Java EE is a very, very complex framework that gives you very little. The only we don't all know about. Yeah. So the only thing worse than Java EE is what you would produce if you tried to produce Java EE yourselves. Okay. So I'm not leaving myself out of that equation, right? So all of us. Yeah. So there's lots of value. So if you go use Java EE and you get EJBs or whatever, it forces a single threaded paradigm on you. So you avoid concurrency, right? So that's where your life, even though it's a complex thing, and even though some of the vendor products you don't really want to go near, it is a place to be if you don't want an interesting life. Okay, so we're going to roll our own, and so in this particular case, we're writing a little language voting system. Okay, it's a totally unbiased voting system here. Just because it's got code here, if the language starts with a capital letter G, yeah, ignore that. That's just in your imaginations that might be biasing the results somehow. Okay. So how does actors work? So actors are expecting to get messages to come in. So we're going to go write an actor, we're going to extend a class, and we're going to allow ourselves to get two different kinds of messages. Either a string, which is a language that someone's voted for, or we've actually got polling booths coming in as well that gives us a whole list of strings. Okay. And what do? Well, for the polling booth entries, we just go through each of the languages that come in and process the vote, and we tally them all up here. Now, so that's now an actor. If that's a class, we create an instance, and we go start. We've got an actor running. Okay, and we can now just send it messages. So we start sending it messages or lists of messages, and then we can stop and join, and it'll print out. You'll get a list of all the languages that were voted for. And we can see a couple of Groovies and a Go here. So I don't know what happened to some of the other languages that were voted for. Must have been a glitch in the system, I'm not really sure. So there's other different styles of that we could have chosen. So yeah, I got rid of that looking for letter G, by the way, in the code. Some people thought that was biased, so this one doesn't look for the letter G in the languages, so in case you're worried about this being biased. So this one here is using the DSL style. So in a lot of things we try to do when we're using Groovy is actually, get rid of some of the boilerplate noise. So we've written inside GPars a little DSL language that lets you create things so you don't ever need to see that class-looking thing we saw on the previous slide. Okay. So in this case, we just say, yeah, we're going to create an actor and we're going to loop through and do things, and basically, yeah, when the things come in, we're going to react and print stuff out, and yeah, this is. Well, I skipped one little bit. So we're actually creating two actors here. Turns out, if you've got an actor that's very, very simple, and all it does in life is accept a message and do something, you can use a reactor. Okay? And so there's an implicit parameter here. Groovy uses IT as the this, or the implicit parameter. So this goes and creates an actor and runs it. So we didn't need to do the instance creation, we didn't need to do start, we've got an actor running. And now we create another actor and we actually feed it data, and then we can do things here, right? We're actually sending the data here. Yep. Actually, I've probably even left one little bit of info out in this one. So there's a send and wait that'll actually do things synchronously. And if we want to do things asynchronously, then we actually just, in our code, we just do a react, and that'll now have a loop for us where we're now waiting on a message and we'll do something. Okay, does that all sort of make sense? So it's just a little DSL that saves you writing all the classes we saw before. And if you don't like that flavor, there's yet another flavor which lets you write POJOs, plain old Groovy objects, and you just annotate them with active method and active object. And you create that, you just create it as if it was a normal Java object everywhere, and everywhere where you did active method, it basically puts a messaging layer at the front of that. Okay, so there's three different styles, and I got some people thought that I was only counting letters and Y was a bit biased, languages that ended in Y was a bit biased, so I got rid of that in this implementation in case you were worried about this being a biased implementation. Okay, so what we do is we just create a new object. We don't need to say .start or anything, so we're treating it like a pogo, and we just call its methods as if it was an object, and this is all using message passing underneath the covers. So three different flavors, and yeah, showing you a little bit of the complexity that comes about when using actors, because you've got decisions to make of which of these styles, whether you've got stateful or stateless and things. It actually chooses different implementations underneath the covers for you. So there is some complexity. You don't want to do actors without your thinking cap on, but there's some really nice properties. If you do need to use actors, some really nice properties that come about for these. Now you can still get deadlocks, you can still get live locks, you can still get a range of other things, so you've still got to cater for all those sorts of things. Okay, agents. Agents are someone who's going to worry about synchronization for you. So I told you not to use Synchronized before. Well, this is sort of the cop-out. This is what we're going to do is some other object is going to do all that sort of ugly stuff for us, and we'll just tell it the business logic that we want to eventually happen, and it goes and works out how to do all that sort of stuff. Now, I don't want to spend too long on this slide. There's lots of examples of agents, but basically we've got a list and we're trying to add things to it, and we're going to do that from a bunch of different threads. So I've gone old school, gone thread.start here, and we're firing up a bunch of threads, and each of the threads is just going to go and try to update things. And what they're really doing is they're sending, speakers is our agent. It's an agent that handles lists of things, and they actually send it commands. So it's like a command pattern. And so we're going and telling the agent, yeah, I want to update a value. Yeah, I want to update a value. Yeah, I want to read a value. I want to do this. I want to do that. And this is just chunks of code. These are closures. We're passing that to it, and it goes and does everything. And it goes and sequentializes all the statements that are coming in, all the operations that are coming in. And it actually does it in a very, very smart way. It's not, if you just did full serialized synchronization here, it wouldn't be very efficient. So it actually does some smart analysis of what it can do and what it can, can it have many readers, because there's no writers at the moment and things like that. There's a few things that are going on under the covers. You don't need to worry about that. Okay. Software transactional memory is another thing that's available to you. And this is transactions percolated up. You've probably seen transactions when you're dealing with databases. This is the same concept, but happening at your code level. Okay. And again, there's some really smart, so there's languages that have good support for this. And there's some really smart algorithms that they typically use. And there's some nice properties when we do this sort of thing. So won't have time to give this full justice today, but we're creating some bank accounts and we're trying to transfer a certain amount from one account to another. So if we're going to transfer $10 from this account to this account, that's going to work because they've both got $20 in to start, and by the end of it all, I don't have an assert on this one. One will have 10 and one will have 30. If I said let's transfer $30, obviously that's going to fail because the from account doesn't have enough funds in there. You don't need to worry about. You just can write statements that ignore the fact that transactions are going on, provided you're using this framework, and there's some specifics. I won't sort of go into all the detail. You basically have atomic sections, and your account has references to its balance. You go and do all these things. If something goes wrong, the framework is going to roll back stuff for you. Okay. Now, this looks at surface value like a wonderful, beautiful thing. It's getting rid of a whole lot of complication that you get in these concurrent systems, but there's actually quite a lot of complexities in terms of, like in databases, you can get, there's a whole lot of tricky edge cases if you're trying to do things really, really efficiently. All of those come up again. So I'm not going to try to scare you away from this. If you've got a fairly simple cases, this can be a useful technique, but you really do need to have your thinking cap on because there are some real tricky, subtle complexities that can happen in these sorts of environments. Be good if I had some more time to go into that, but we won't skip over that. I'm going backwards. I wonder it didn't seem right. So in the remaining 5 minutes that I've got, I just wanted to actually show you the second of these examples, and I'm going to skip through to this. So this entire example is up on the Groovy website. This actually was stolen directly from Guy Steele. He did a keynote at Strange Loop conference a couple of years ago, and he was on the Fortress programming language. It was very, very interesting. Go and look at his slides, and you can go through. It's got a whole bunch of nostalgia about filling in card decks and things as well at the start. Just skip over that, jump along to slide 52, and you can go through and look at how to do this problem using Fortress. But we're not going to learn Fortress today. It's got nice wacky symbols and all sorts of things. We're going to look at how to do this problem using Groovy. You could do it in your own language as well. It's fairly simple to do. What we want to do is we want to take a sentence, this ultimately could be a huge file sort of things, and split it into its words. Very simple concept. Here's one algorithm that does it sequentially. Okay, so I just start off with an empty list of words, and I remember, word happens to be the word I'm remembering now or I'm processing now, and I just jump along, and whenever I see a space, I either, if I've got some stuff that I've remembered on the current word, I'll store that in the list. And otherwise, I'll just add the character that I'm looking at, so I'm doing a character at a time, onto the word I'm remembering. And at the very end, if there happens to be some stuff left over, I'll add that to the list as well, just to do the end case. Okay, so that's a sequential version. And I guess graphically, we're kind of doing this. So we've got a result, and we're kind of aggregating and going all along. How do you think this particular algorithm would go if we say, okay, I've got 100 cores available to me, let's just farm it out to all those 100 cores. What would you expect to happen? One core is going to get busy and 99 cores are going to get very lonely, aren't they? Because each result is waiting on the previous result. Okay, so it's sequential. So you might think, okay, well, it's sequential. I've got to go and use those actors because they're the stuff to do the complex stuff, right? Is that right? Well, no. What you typically do first to get best bang for buck is see if you can tweak this algorithm to turn it into a data parallelism problem, a MapReduce or something like that. If you can, your life will be simpler, and other times you will use actors. And I don't want to turn you off actors, but don't jump in them as always your first tool. That's all I'm trying to say. Okay, so this is what we're going to do is tweak this algorithm now. So how can I change this algorithm so that any of my cores can do a chunk of the work? Okay, well, what we're going to do is we're going to split the thing up, and once we get to a small enough size, it typically works out best to go and sequentially solve that piece of it. Okay. So what we need to do is, as we're solving this piece, remember the left and right boundary conditions. All right, that's the information I don't have when if I was just given one chunk and I don't know what's on the left of me, I don't know what's on the right of me, I can't really do what I need to do. So what I'm going to do is remember the left condition, remember the right condition, and the stuff that's in between those, I'll process all of those. So I'll get a list of words that I do know about, plus a bit of stuff on the left I'm not quite sure of, a bit of stuff on the right I'm not quite sure of. So that's what we're going to do. So we're actually going to build a little mini domain model to capture that. And basically it's going to let us result like this. Process the result like this. So what we're going to do is, as we're processing one of these things, we're going to, we just get a whole bunch of characters, we're going to store it in a chunk. We can't really tell much about this because we don't know what's on the left or on the right. If we've found some words, we'll stash away those words and then we'll remember, oh, over on the left, there's something, I can't really work that out yet. Over on the right, there's something, I can't really work that out yet. But I can now process each of the pieces. So that's good. The next problem I have is I need to aggregate them all together at the end. And it turns out I can do that with this domain model. So if I've got two segments, what I can do is the stuff on the end I still don't know about because I don't know who's on the left of me. So I'll just remember that. The stuff that's on the very right, I'll just throw that as the other boundary condition. And all the words you found here and here, we'll concatenate those together with adding these two little bits together with a slight caveat in that if both of these are empty, I'll throw it away, basically. Okay? So it turns out I've now got a way to solve a piece, now aggregate the results together, and here's the code that you'd use for your domain model. So this maybe word is the thing that decides whether or not I've got the empty thing to throw away or I've actually found a word. And I've got a chunk which I can add other chunks to or other segments to. I've got a segment that I can add other chunks or segments to. I've got a zero element. What's that all about? Well, over in this graph here, because I don't know, when I'm splitting things up, I don't know whether there's nothing on the side of me or not. I've got to be able to handle the case of I'm on the boundary condition. So we need a zero. And because we don't know, are we the left piece or the right piece or whatever, we don't know that either. So we actually need associativity. We'll come back to that. So that's our algorithm, and now we can rewrite the original sequential thing you saw in a slightly different way. This is just fold. So to process a character, if it's an empty string, I store it away as a segment, otherwise I store away the chunk as the character. Now I can just do a fold or an inject on that, and that'll do my sequential version now. Okay? So I don't have any parallelism yet, but I've actually tweaked the original problem to look like this, and I can do an assertion here. There's some nice properties about this. It's associative. That means it doesn't matter what order I do these things in, it's got a zero. And if you want to impress the workers back at the office, that's called a monoid. Not a monad. That will either delight or scare your other co-workers, so don't use that word unless you want to have that effect. Now, I've got samples of this using DataFlow and MapReduce and filter and whatever. I'll let you go and look at those on the web. I'll just show you one of those. Actually, let's skip to this one here. So what I need to do is I need to partition my input, which just takes the original thing and blocks up into chunks of 10, and then I just say, oh, in parallel, do a MapReduce on those. And that's my problem solved. Does that look like a nice way to solve these sorts of problems? Yeah. So with a few tweaks, you can take something that's inherently sequential and turn it into this. Okay, that's all I've got time for. If you want to see all the other examples of that particular problem or of the dotting philosophers, it'll be on GitHub. Okay, thanks very much.